Let's take a look at number 11 in section 4.7. So in this problem, our task is to design a rectangular industrial warehouse consisting of 3 separate spaces of equal size as shown in this figure. So they give us this figure. They even label, so here's the perimeter of the entire structure. You're looking down from above at it, and then we've got these walls here that will separate into 1, 2, 3 separate rectangular spaces of equal size. Each space will have this dimension here, this length, if you will, x, right? So these are all x long, and then the width of each individual space is y, and so each of these are y, right? And so that's important in this problem. They give you that as your dimensions. So the wall material costs $500 per linear meter, and your company allocates $1,200,000 for that part of the project involving the walls. So we get to spend $1,200,000 to construct the walls of the structure. Which dimensions will maximize the area of the warehouse in this case? Okay, so they do want you to give exact answers, use symbols, symbolic notation, and fractions where needed. So let's see how that plays out. First of all, I'm going to let A be the area of the warehouse, okay? Because the question is, again, to maximize what? The area of the warehouse, right? We're going to maximize the area of the warehouse. So what is the area of the warehouse? Well, that's all 3 of these separate spaces, right? So what is the length? It's not y, but it's 1, 2, 3y, isn't it? It's 3y long and x high, or 3y wide and x in length, whatever. So 3y times x is 3xy. So the area is 3 times x times y. That will give us the area of all 3 of these separate spaces, but that's the entire warehouse, right? So that's what we want to maximize. Okay, so what's the constraint? Well, the constraint is cost, right? We just can't build it as big as we want. There's a cost per linear foot. Sorry, I keep saying foot. I even wrote it there, meter. And we have a limit of this amount, right? $1,200,000. Again, your problem might have slightly different numbers, but the problem will be solved the same way. So the constraint is cost. Right? So what is the cost to build this structure? It's $500 per linear meter. How many meters to construct the walls? How many meters to construct the walls? Well, we need how many x lengths? Let's count them. I need 1, 2, 3, 4. Each of these lengths right here will be x long. So I've got 4x. So I've got right here 4x. How about the y length? So let's count them. I've got, this is y1, this is 2, this is 3, and then 4, 5, 6, right? So I've got a total of 6 y lengths. So the total amount of walls we would need in terms of x and y is 4x plus 6y. That's the meters, right? And then it's $500 per meter. So if we multiply that by 500, that will give us the cost in dollars to construct the walls. And what does that have to equal? Well, our total budget, which is $1,200,000. So that's the constraint equation. So what I'm going to do again is we're going to maximize this function here. It's a function of 2 variables. So again, I'm going to solve for one of my 2 variables, plug into this formula so that I can then use the derivative and find the maximum for the area of the warehouse. All right, I'm going to solve for y. First, I'm just going to, instead of distributing the 500 through, I'm just going to divide both sides of my equation by 500. And 1.2 million, or 1,200,000 divided by 500 is 2,400. And so I get 4x plus 6y is equal to that. I can subtract 4x, divide by 6, right? 2,400 divided by 6 is 400, and 4 divided by 6, 4 6 is 2/3, simplified down. So there's y in terms of x, okay? And then what about x? What is the constraint on x? Well, x can be as small as 0, and of course that would be a poor design. As x goes to 0, then our y lengths are getting longer and longer. In the extreme case, when x goes to 0, we really have no enclosed space, but we have 2 walls, right, that are 3y long, right? built right next to each other, right? And so that would be the extreme case. Of course, in that case, then we can see from this equation, if x goes to 0, that we would have 6y equals 2400, or y equal to 400 in that case. The other extreme is I can let y go to 0, right? If y goes to 0, then we have 1, 2, 3, 4 x lengths, right? Walls, we have 4 walls right next to each other, right? Again, the area of the warehouse would be 0. That would not be a good design, but we could do that. We'd probably be fired, but we could do that. And in that case, if y goes to 0, notice 4x is 2400, and if I divide 2400 by x by 4 rather, I get 600 for x. Of course, that's when y is 0. So x ranges anywhere from 0 to 600. Of course, y ranges from 0 to 400. But since I solve y in terms of x, there's the restriction. Okay, and so we can now take this expression for y, as we've done so many other times in other problems, and plug it in, replace that with that. And what do I get? 3x times, made a mistake here, but plug that in there, 400 minus 2/3 x. And then I'm going to distribute 3x times 400 is 1200x. 3x minus 2/3 x, the 3's cancel, I just get minus 2x squared. So here's my area function. Pretty simple function. Find the derivative. The derivative is easy, right? Get 1200 minus 4x. It should be pretty simple. And then the derivative is clearly 0. I hope you can see when x is equal to 300, right? When x is 300, we would have 1200 minus 1200. So when x is 300. So that's our critical point. If I do a table of values for x, remember x we said goes from 0 to 600. We've already discussed that, and you can plug into the formula for the area here. You can plug it into this area formula and confirm. But if you plug in x equals 0, you get 0. If you plug in x equals 600, you get 0. We already discussed what would happen. Just building walls side by side will make the area of the warehouse 0. So do not design it that way. However, when I plug in x is 300, I get this quantity. If I plug in x equals 300 in the area, I get this quantity. That's a maximum, therefore, right? Because we've checked the endpoints and the only critical point on that interval. And so that's going to give us the maximum. Notice when x is 300, if I plug in 300 here, I'll get 400 minus 2/3 of 300 is 200. 400 minus 200 is 200 meters. So therefore, we know that we will have the maximum area. The dimensions that will maximize the area of the warehouse are when x is 300 meters and y is 200 meters. And in that case, there was another question there. The maximum area of each compartment would be what? Well, the maximum area is 180,000 square meters. But remember, there are 3 different separate spaces, 3 different compartments, right? So divide 180,000 by 3, and you get 60,000. There's the area of each. The maximum area of each. Okay, I hope this is helpful on this one. Again, as always, if you have questions, let me know.